So in this lecture, we want to develop one of the central results of statistical mechanics, and that's we call the Boltzmann distribution or Boltzmann factor, telling us about probabilities in a non-isolated system. So let me just remind you where we've been so far. Previously, we've been talking about isolated systems. So we had, a bunch of particles which had to be distributed between energy levels, and the total energy of that whole system was fixed. So that was an isolated system. So it had some fixed energy, couldn't exchange any energy with the outside. And in order to analyze that system, we sort of wrote down all the possibilities, all the different ways that the particles could be distributed. And then we said, we made the fundamental assumption that all of the microstates of the isolated system are equally likely. So they were all equally likely, and that's how we were able to calculate probabilities in this system. What I want to think about now is, let's go one step beyond this and think about, what if my system is not isolated, but it's able to exchange energy with something else, in particular a reservoir at some temperature. So I've got some system and it's in contact with some large reservoir at some temperature T, and I want to think about, how do I analyze the probabilities in that system? So it's not isolated anymore, and that's going to add a little bit of extra complication to our calculations. So this is going to lead to, that's the main difference from what we've done before, is that the system is no longer isolated. It could be in contact with a different system which is at some temperature. And we're going to, again, think about the relationship between the probabilities in this system which is not isolated. So that's the plan for this lecture. So as a warm-up, let's go back to this system, a three-state system which we analyzed last lecture, and we put the constraint that the total energy here was set equal to 2 epsilon, and I had 4 particles, which I'm calling, let's say, distinguishable A, B, C, and D. These are the atoms that are being distributed among these 3 energy levels here. 0, epsilon, and 2 epsilon. So this is an energy level diagram here, energy going up. Okay, we worked out, just by thinking about all the number of ways that I could accomplish each of these, that there's 2 distinct macro states. So one I'm calling k equals to 1, one I'm calling k equals to 2. So there was the multiplicity of the total system here. I'm not quite sure what to call it. I guess let's just call it omega of k equals to 1. Was 6. There were 6 ways to achieve this, and then there were 4 ways to achieve this. And so the probability that this occurs was 6 out of 10, which is 60%. Let's call it P1. And the probability that this occurs is 4 out of 10, which is 40%. Whoops. Okay, so that's where we were. Now I want to start asking a different question. So, a new question. I want to ask, what's the probability that atom A has energy 0 or epsilon or 2 epsilon? So I want to focus on one of those particular atoms, atom A, and I want to know what's the probability that it has some energy. So maybe, for example, I'm focusing on, this could be atom A. I want to know what's the probability that it's up there in energy with energy epsilon. So in order to tackle that, maybe I'll do something which is sort of unusual. Let me write down all 10 possibilities here. So here are all the microstates, all those 10 microstates of the system, and I've labeled the individual atoms and what energy state they're in. Sorry, let me make it clear that there's a line here. So there's 5 there on the top row and then 5 on the bottom row. Okay, what's the probability that atom A has energy epsilon? Let's just count them up. So this is going to be the probability that the energy of atom A is equal to, well, let's start with 0. Let's think. So how many ways are there that A appears in the lowest one? So there's one here, 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 and here. Sorry, and these three. Or all three of these. So all of those states which I just circled, A has energy 0. So there's 1, 2, 3, 4, 5, 6 ways of doing that. Let's do the others. What's the probability that atom A has energy epsilon? Let's maybe circle them in a different color. Let's do blue. So that would be these three sitting here, right? There's 3 of those. So that's 3. And then what's the probability that atom A has energy 2 epsilon? There's only one left. It's this one here. So it's equal to 1. Still adds up to 10, of course, because I still have the same number of microstates. And I'm still doing the same thing. I'm just counting all of these microstates. And remember that all 10 of these are equally likely. So if all 10 of these are equally likely, sorry, this should be 6 out of 10, 3 out of 10, and 1 out of 10 will be the probabilities of each one of those. So this is the kind of analysis we want to do. We want to ask, what's the probability that atom A, which is a part of this larger system, what does it have? What energy? What's the probability that it has energy 0, energy epsilon, energy 2 epsilon? But eventually I'm not going to be able to write out all of the states, so we want to think about what's a better way of doing this. So on the previous slide, we worked out these probabilities just by writing out all the microstates and counting. But let's think about a faster way, or a way that will work if I can't just write out all the possibilities. And that is, I'm dividing my system of 4 atoms into a subsystem, which is going to be atom A, and then the remaining atoms, which I'll call the remainder, that'll be B, C, and D, the other 3 atoms. Okay. So, for example, maybe this is atom A, and then the other 3 I'm lumping together and treating them like a remaining system. Maybe this one, again, is atom A, and then the other 3 are the remaining system. What I'm most interested in is the number of ways that I can range the remaining 3, keeping atom A in some state. Okay, so what I really want to know is, what is the multiplicity of the remaining atoms? The R stands for the remaining atoms, when the energy of the system A is equal to something like 0 or epsilon or 2 epsilon. So the multiplicity of the remaining system, what is that? Okay. Maybe the easiest one is to do the last one here. So that's where I have my atom A is up in the 2 epsilon state, and then I have 3 remaining atoms, and I have to choose all 3 of those to be in the 0 state. So it's 3 choose 3. 3 remaining atoms, and then I'm choosing 3 to be down in the 0th energy level. So this is 1, so there's only one way of doing that, right? Let's think about this one. How about if atom A has energy epsilon, what do I have to do? Then I'm in the situation kind of shown over here. So if atom A has energy epsilon, then maybe, for example, this would be A. The other 3 are the remaining ones. And how many ways can I arrange those? I have to pick one of those remaining 3 to be up in with energy epsilon. So I've got now 3, choose 1 to be energy epsilon. So that's 3. And then the last one is the more difficult one. So I've got Now, what's the probability that the atom A has energy epsilon? So now this could be A. The other three here are the remaining pieces. So I could have the situation on the left where I have to choose 3, choose 1. I have to pick 1 to be in the lowest state here. So I pick 1 to be the lowest in the lowest state. There's 3 ways to do that. But then I have another possibility, which is I could have the one on the situation on the right there, where I have A down in the lowest level, and then I have to pick 1 to be up in the highest level. And there's 3 ways to do that, right? So it's 3 choose 1 plus 3 choose 1. So I pick from those 3, I either pick 1 to go in the level 0 or up at the top there, right? So 3 choose 1 plus 3 choose 1, that's 6. And you see the numbers that we're getting here are exactly the same numbers that we got before just by counting. So the probabilities here are related to the multiplicity of the remaining part of the system when that atom is in a particular state. And that's the idea that we want to make more quantitative. So probabilities that atom is in some state, let's call it psi, is related to the multiplicity of the rest of the system, or the remaining part of the system, in this configuration. Okay, so now let's go away from this toy example and try to do a more rigorous example involving maybe many particles, but the idea is going to be the same.